Your lecturer is Professor Richard J. Heyer. Dr. Heyer is Professor Emeritus in the School of Medicine at the University of California, Irvine, where he has been teaching and conducting research since 1984. He received his PhD in psychology from Johns Hopkins University. Professor Heyer's main research interest is the structural and functional neuroanatomy of higher cognitive processes, especially intelligence. His work has been featured on Nova Science Now, NPR, CNN, and CBS Sunday Morning, and in numerous newspaper and magazine reports, including those in Newsweek and Time. In 2009, Dr. Heyer summarized his intelligence research for the public in an article in Scientific American Mind. In 2012, he received the Distinguished Contributor Award from the International Society for Intelligence Research.
Welcome to our course on the science of intelligence. We're going to explore some of the things we know about intelligence and some of the things we're learning. But first, I'd like to introduce you to this young man. His name is Daniel Tammet, and he's an autistic savant. Savants are quite rare. They usually excel at a narrow mental skill to a level that often appears to be in the genius range, but they also typically have low IQ. Daniel's unusual because he has high IQ. He's good at remembering numbers and learning foreign languages. It took Daniel only a week to learn Icelandic, a feat he demonstrated by being interviewed on Icelandic TV in Icelandic. But he's perhaps best known for a public demonstration of his memory for the digits of pi. As you know, pi is the circumference of a circle divided by its diameter. It's always the same number, and it's an infinite number. It's 3.1415926, and so on. So how many digits did Daniel memorize for his public demonstration? You can already guess it was a lot. But was it 840, the equivalent of 120 phone numbers without area codes? Or was it over 2,000 digits? Or could it possibly be over 22,000 digits? The answer is 22,514. It took Daniel 5 hours to recite this string of numbers while checkers followed along using a computer printout. And just to make this feat even more interesting, Daniel apparently has a condition called synesthesia, a condition that blends the senses so sounds or numbers, for example, are perceived as colors or even odors. Daniel says he sees numbers as colors and shapes. So when he's recalling a long series of digits, he's seeing in his mind a changing landscape of shapes and colors that he translates back to digits. Now, the neural basis for this condition is unknown, and its role in memorizing such a long series of numbers is not clear at all. And now I'd like to introduce myself. I'm Richard Heyer, and my interest in intelligence really began in the early 1970s when I was studying psychology in graduate school at Johns Hopkins. At the time, there was a dramatic shift away from the behavioral theories of B.F. Skinner, and cognitive psychologists were making very interesting inferences about how brain processes worked to process information. I was interested in why people differ on things like personality and reasoning ability. And I've been doing research on intelligence ever since. I'm excited to have this chance to discuss it with you. We'll focus on how scientific research is done on such a complex topic and on actual data from research studies. As you'll see, we've already learned a lot, but many mysteries remain, and most of them are surrounded by controversies. In this lecture, we'll examine some basic concepts necessary for defining and measuring intelligence, and I'll present a tentative answer to the question, where in the brain is intelligence? And finally, we'll consider what the new science of intelligence may mean for you. But first, I'd like to introduce you to another individual with extraordinary mental ability, Kim Peek. Kim was the model for the Rain Man character in the 1988 movie with Dustin Hoffman. Kim passed away in 2009, but he was quite well known for his appearances before audiences who tested his memory for facts, like when was King Henry VIII born, and when and where did he die? Now, in fact, Kim could answer this kind of question for just about any historical figure or event. And he could answer many other questions based on his ability to recall 7,600 books, which he had read by paging through them and scanning each page very quickly. Kim had a low IQ and could not work or care for himself, but he had an amazing memory and recall ability. Now, how he did this is not understood, but clearly extraordinary memory is not the same as high intelligence. A third example of a person with extraordinary ability who may or may not be considered intelligent is the human iPod, pianist Derek Pavarottini. Derek is blind, and his mental ability is so low he cannot care for himself. However, he can listen to any piece of music just once and then play it again in any musical style. His special talent is focused and limited to music, but in this case, musical genius is not the same as being highly intelligent. Here's another example, Alonzo Clemens, the animal sculptor. Alonzo has low IQ, but he can look at an animal briefly and then create realistic sculptures of the animal like these. So we have Daniel, Kim, Derek, and Alonzo. These examples of really extraordinary mental abilities raise two obvious questions. How do they do it? And why can't I? There's also a third question, given their amazing mental abilities. Why aren't they super intelligent? Albert Einstein was, of course, pretty smart, possibly one of the great intellects of all time. But he couldn't do what Daniel or Kim or Derek or Alonzo could do. What does this tell us about defining intelligence? Before we answer, here's another thing to consider. This person is watching a ball come at him at over 100 miles an hour, and he's calculating where to run, where to stand, how to swing a racket so he can hit the ball back to a specific spot, all within a few seconds. Is this kind of athletic ability also a kind of intelligence? Some psychologists may think so, but as we'll see shortly, there's a definition of intelligence that's the basis for most intelligence research, and that definition would not include athletic skills. And here's a special case. Watson, the IBM computer that beat two all-time Jeopardy champions. The rules were that Watson could not search the web. All information had to be stored inside Watson's 15 petabytes of memory, about the size of 10 refrigerators. Here's an example of a question. In the category Chicks Dig Me, the answer is, this mystery writer and her archaeologist husband dug to find the lost Syrian city of Arkesh. This sentence is actually quite complex for a computer to understand, let alone answer the question. In case you're still thinking, the answer in the form of a question for Jeopardy is, who was Agatha Christie? Watson answered this faster than the humans, and in the actual match, Watson trounced the two humans. Does Watson have the same kind of intelligence as humans, or better? This is a harder question than asking if athletic skills are part of human intelligence. Now, these examples illustrate some of the challenges of defining intelligence. So now let's talk about how intelligence is defined and measured. Here are some definitions. The first from the American Psychological Association Task Force on Intelligence. Quote, individuals differ from one another in their ability to understand complex ideas, to adapt effectively to the environment, to learn from experience, to engage in various forms of reasoning, to overcome obstacles by taking thought. End quote. Other definitions of intelligence: what you use when you don't know what to do, or, how about this one? The opposite of stupidity. My favorite: intelligence is individual differences in learning, memory, and attention. Here's a widely accepted definition among researchers that was proposed by Professor Linda Gottfredson. Intelligence is a very general mental capability that, among other things, involves the ability to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, and learn from experience. It is not merely book learning, a narrow academic skill, or test-taking smarts. Rather, it reflects a broader and deeper capability for comprehending our surroundings, catching on, making sense of things, or figuring out what to do. Now, the main element common to all definitions of intelligence is that it's a general ability. IQ, mental ability, intelligence are all used in the same way to describe this general ability. Here's an important thing to remember about defining intelligence. In every branch of science, definitions of basic concepts evolve over time and get more and more precise as measurements get better and allow finer-grained questions. This is why the definition of a gene, for example, is changing as we learn more about the human genome based on DNA sequencing. This happens in every scientific field. And all the definitions of intelligence have the same inherent challenge for researchers. How do you measure intelligence to do empirical research? We expect as measurements improve, the definition of intelligence will become more precise. Now, we'll detail measuring intelligence and some controversial issues about IQ scores in the next few lectures. But here's an important concept about intelligence as measured by IQ tests that I want to review here. IQ scores are derived from a battery of tests, so the single IQ score actually represents a range of mental abilities. That's why it's a good measure of general intelligence. IQ scores for very large random samples of people are normally distributed, and I want to review some properties of a normal distribution. Many variables are normally distributed in a large population, and these properties are the same no matter if we're talking about height or income or intelligence. A normal distribution is also called a bell curve. Let's look at the IQ normal distribution. IQ scores typically have a mean of 100 and a standard deviation of 15. 50% of people score above 100 and 50% score below 100. Average IQ is 85 to 114. 68% of people fall into this range. IQs less than 85 are in the lower end of the distribution, and we have 16% of people have scores of 85 or lower. IQ scores of 115 to 129, this is a higher normal range, and there are 14% of people in this range. IQ scores between 130 and 145, now we're talking about the top 2%. These scores are higher than 98% of the population. When we talk about IQ scores over 145, this indicates the top 0.1%. Now, IQ scores predict general learning ability. Here's how people at different IQ levels learn. As you can see in this illustration, people with IQs below 80 or 85 generally learn slower and require more concrete step-by-step instruction. People with IQs over 115 generally learn more abstractly and seek out information on their own. In the middle IQ range, many individuals certainly can learn complex material, but it may take longer with more individual instruction. Keep in mind that these are not perfect relationships, and there certainly are exceptions to these generalities. Now, IQ predicts many real-world things. As we'll see in subsequent lectures, IQ scores predict not only things like education level, income, and job performance. IQ also predicts health and even mortality. But IQ does not predict many other important things like happiness, mental illness, honesty, or being a nice or likable person. And I'm sure you can think of your own examples. So how do we reconcile intelligence as a general ability with the specific abilities of savants? Here's what researchers have learned. There are many mental abilities, some very specific, like tests of spelling or the ability to mentally rotate 3D objects. Other tests assess more general abilities like memory or problem solving. We have over 100 years of research about how such tests relate to each other. Here's what we know. Different mental abilities are not independent. They are all related to each other, and the correlations among mental tests are always positive. That means if you do well on one kind of mental ability test, you tend to do well on other tests. This is the core finding about intelligence, and as we'll see throughout this course, it's the basis for most modern research. Now let's look at this a little closer. The relationship among mental tests is called the structure of mental abilities. To picture this structure, imagine a three-level pyramid. At the bottom, we have a row of many different tests of specific abilities. In this illustration, there are 16 different tests. At the next level up in the pyramid, tests of similar abilities are grouped into more specific factors like reasoning, or spatial ability, or memory, speed of information processing, and vocabulary. In the illustration, tests 1, 2, and 3, for example, are all reasoning tests. Tests 7, 8, and 9 are all memory tests. But all these more specific factors also are related to each other. This is a key finding demonstrated over and over again. It strongly implies that all the tests and factors derived from individual tests have something in common. And this common factor is called the general factor of intelligence, G for short. G sits at the very highest point on the pyramid. G was first described by Charles Spearman over 100 years ago. G is the basis of most definitions of intelligence used in research. It's not the same as IQ, but IQ scores are good estimates of G because most IQ tests are based on a battery of tests that sample many mental factors. Many of the controversies about intelligence have their origins in confusion about how we use words like mental abilities, intelligence, the G factor, and IQ. Here's a diagram that may help clarify how I'll be using these words throughout this course. We have many mental abilities, all the things you can think of from multiplying in your head to picking stocks to naming state capitals. The large circle represents all mental abilities. Intelligence is a catch-all word that means the mental abilities most related to responding to everyday problems and navigating the environment. The circle labeled intelligence is smaller than all mental abilities. IQ is a test score based on a subset of the mental abilities that relate to everyday intelligence. The IQ circle is a fairly large part of the intelligence circle because IQ is a good predictor of everyday intelligence. And finally, the G factor is what's common to all mental abilities. The G factor is a fairly large part of IQ. Whereas everyday intelligence and IQ tests can be influenced by many factors, including social and cultural ones, the G factor is thought to be more biological and genetic, as we'll see in later lectures. Now, the savant examples described earlier speak to the level of very specific abilities with little, if any, G in many cases, like Kim and Derek. They show that powerful independent abilities can exist, but they also show the problems when G is lacking. The IBM computer Watson demonstrates a specific ability to analyze verbal information and solve problems based on the meaning of words. This is really an amazing accomplishment, but in my view, this does not show the G factor. Watson is more like Kim Peek than Albert Einstein, at least for now. The savant examples are rare cases. Most people have G and specific factors, and two people with the same level of G can have different patterns of mental strengths and weaknesses on other mental abilities. Now, can we ever hope to learn how savants do amazing mental feats and why we can't? Is it possible that we all have the potential to memorize 22,514 digits, or the potential for musical or artistic genius? And why are some people smarter than others? Does everyone have equal potential for learning all subjects? The answers must have something to do with the brain. But where in the brain is intelligence? We can ask this about G and about specific factors. Is one brain organized to be better at math and science and another brain better at writing or creativity? If so, how did these brains get that way? What is the interplay between genetics and experience as they influence intelligence? Such questions have been my research focus for nearly 4 decades. I'm going to detail genetic and brain imaging studies of intelligence in subsequent lectures, but here's a preview about what smart brains may look like. Back in 1988, we did the first brain imaging study of intelligence. We used an imaging technology called positron emission tomography, or PET, P-E-T. PET is a way to measure glucose use in the brain, and we did this while people worked on a test of intelligence to see what areas of the brain lit up during the problem solving. Here's an example of the kind of problem from the intelligence test we used during the PET scan. In the top box, you see 8 symbols. They're arranged according to a pattern or a rule, but notice there's an empty spot in the lower right corner. Once you figure out the rule or the pattern, you can choose the symbol that goes in the lower right from the 8 multiple choices in the boxes below. In this case, if you add the symbols in the top row to the ones in the middle row, you get the symbols in the bottom row. So the answer is number 7. Notice the pattern is the same if you add the left column to the middle column to get the right column. Now, this is a test of nonverbal abstract reasoning. Scores on this test are highly correlated to IQ scores. This test is regarded as a very good measure of the G factor. So our question was, what brain areas are working while solving these problems? When we analyzed the PET scans, we found something quite surprising. Look at this image of 2 PET scans. The image on the left shows the person with the lowest intelligence test score, and the image on the right shows the person with the highest score. Even without any detailed explanation of what PET images show, you can see they're really quite different. And it's not the difference we expected. And 25 years later, we're still working to understand this difference. Now, we're going to save the detailed explanation for this result for later in the course, after we've covered more background material. There are now many brain imaging studies of intelligence, and I'll tell you about some of the most intriguing ones in later lectures, because imaging technology has really dramatically changed intelligence research. For now, here's a brief summary of a possible answer to where in the brain is intelligence. It's called the parieto-frontal integration theory, or PFIT model. It's based on a review of 37 imaging studies of intelligence. The PFIT identifies a network of brain areas as shown by the colors in this illustration. The key areas are mostly in the parietal lobes and in the frontal lobes. The colors show specific brain areas, and we'll discuss this in much more detail in a later lecture. I just want to give you the main idea here, and it is that intelligence may depend on how information flows around this network. And if we could measure this information flow and how it may differ among people, we might devise a completely new way to measure intelligence from brain imaging. We're actually working on that, and here's a preview. In this movie, you will see a person on the right and a person on the left both solving a complex problem. Person on the right is very good at problem solving, and the person on the left is not so good. And what you're seeing is brain activity while these people are solving the problems. And the brain activity is showing you the flow of information around the brain from brain area to brain area. And we can compare these two people for the sequence of brain areas that become activated and how quickly they go through the sequence. So does one person have a longer sequence or a different sequence? These are the kind of measures of information flow around the brain that we think can help define intelligence in a new way. And another question we'll be addressing is whether men and women use the same brain areas for intelligence. Here we have the red and yellow areas in this illustration show where more gray matter goes with higher IQ scores. You can see men and women matched for IQ actually seem to have different brain areas related to IQ. And we'll discuss what this might mean when we examine brain imaging studies later in the course. But one point I want to make now is this. Many imaging studies show that intelligence test scores are related to measurements of brain structure and function. This fact virtually eliminates older concerns that intelligence test scores don't assess anything real or important. We're far beyond that controversy. So let's recap. First, savants demonstrate the differences between specific and general mental abilities. Second, defining and assessing intelligence has a long history that's focused on the general factor because it predicts many real-world things. And third, neuroimaging research is beginning to identify these specific brain features that are related to intelligence. This brings us to some big questions. So let's ask, what does the progress in intelligence research mean for you? Can we increase or enhance intelligence? Today, the short answer is no, we can't. You may have heard otherwise because some recent studies suggest that you can train your brain to increase IQ. As we'll see, the research on this is not settled at all. But the longer answer is, yes, we might be able to enhance intelligence in the near future. For example, research is already showing that drugs can focus attention during test taking. Electrical stimulation to the brain improves learning, and manipulating genes improves learning. Keep in mind, all neuroscience studies of intelligence will ultimately lead to attempts to increase both G and even specific factors. Many questions will need to be asked. For example, what will drugs to lessen or cure Alzheimer's disease do if college students take those drugs? Is an IQ pill possible to increase your intelligence? And if there was a pill, if you don't think you'd use it, what about for your children? Would it be cheating to enhance intelligence by altering the brain? Can we assume that more intelligence is always better than less? If so, don't we have a moral obligation to increase IQ if we can? What do you think? We began this lecture by describing people with amazing mental abilities, and we end with speculation about the possibility of increasing intelligence. There's a lot in between, including controversies and debates that could affect education and social policies, and maybe even your own navigation through an increasingly complex world. In the next lecture, we'll tackle more details about how intelligence is measured and focus on IQ testing. And don't worry, it won't matter if you're a good test taker or not.